All right, so we can go ahead and get started. Hello, everyone. My name is Miss Jessica Finn.
And I'm Miss Kelly Van Horn.
And we would like to thank you so much for coming to our first ever virtual science research symposium. We hope that you and your families are doing well during this very crazy time, and we really do appreciate you taking the time out of your day to come and join us and help us to celebrate our seniors and showcase all of the work that they've done in the science research program. The seniors who are in the program, they've been working really hard on their research for the past 3 years that they've been in the program. And even though we can't come together as one whole group and have our traditional kind of symposium, we are really, really ecstatic that we are able to celebrate them and what they've been able to accomplish in this kind of virtual setting tonight. So again, I thank you so much, and we hope that you enjoy.
So as Ms. Finn said, this is our first ever virtual symposium, and we really do appreciate everyone coming out to see all the work our students have done given the current circumstances. This evening, the juniors in our program will introduce the senior presenters. While the students are presenting, you can type any questions you may have into the Q&A, and the students will answer all questions at the end of their presentations.
Up next, our next presenter will be Ganesh Arunachalam, who will be going to the University of Illinois, Urbana-Champaign. He'll be presenting on investigating electronic structure of carbon allotropes using the Y2K computational quantum mechanical modeling.
All right, hello everyone. So thank you, Safi, for that introduction. So my project is investigating the electronic structure of carbon allotropes using the Y2K computational quantum mechanical modeling program. In this past summer, I was able to conduct this research at Princeton University under my mentor, Dr. Nan Yao. So first of all, just an introduction. What is static electricity? Static electricity is essentially the electric charge caused by imbalance of electrons, and it basically is very dangerous to electrical components. While you may experience this while touching another person or touching a balloon, static electricity is very damaging to electrical components because it can cause oxide failure and can degrade electrical components over a long period of time. So this process of static electricity being transferred is called electrostatic discharge. And in circuits, electrostatic discharge is one of the worst things that can ever happen. So one of the things we do to protect against electrostatic discharge is use something called ESD protective mats, or electrostatic dissipation protective mats. And if you look at this diagram here, you have a circuit in the hand here. And what the mat essentially does is it insulates the circuit from any other surface. And since it's insulating the circuit, electricity can't travel through the circuit, since electricity needs to travel between two changes. Electricity transfers as a result in change in potential. And since you have an insulator, the electricity cannot travel through the circuit. So the ESD protective mat really helps while you're working with circuits and protects your circuits from degrading or breaking in any way. However, one of the shortfalls in using these ESD mats is that they're very easy to degrade and they're very susceptible to degradation. For example, if you're working with a circuit, the hot temperatures that come with the circuit can damage the ESD mat. For example, if you're using a soldering iron, it can easily melt the mat. Also, the buildup of dust on the mat reduces the mat's insulation properties, causing the circuit to be more prone to electrostatic dissipation. So overall, I found that these mats have a very low melting temperature, which is kind of surprising because high heats are a very important factor when we're working with circuits. So the fact that these mats couldn't resist those higher temperatures was very concerning to me. So the big question that I had was, why can't these ESD mats resist melting at higher temperatures? So to do this, I created my own independent project to investigate the relationship between melting point and electrical conductivity for the for the optimization of solid structure properties. Essentially, I wanted to figure out if it was possible to have an ESD mat that could still protect circuits while melting at a much higher temperature. So to do this, I realized that I needed to test how different structures of a material would change in response to different crystalline structures. And I needed to see if those different crystalline structures could still be insulating while having a higher melting temperature. So I decided to use carbon allotropes, since carbon allotropes are essentially different forms of carbon in different crystalline structures. However, since they're all made of carbon, they're essentially the same material. And so several carbon allotropes I wanted to test were carbon, graphite, diamond, fullerene, nanotube. And so all these molecules are, all these structures are essentially carbon, but in different crystalline structures. They each only consist of carbon atoms, but the way the carbon atoms are structured results in different properties of each allotrope. So to test these carbon allotropes, I needed to find a way to test their conductivity and their melting point. To do this, I used something called Wine2K. Wine2K is a Linux-based program that uses density functional theory to provide the electronic properties of different crystalline structures. So what I would essentially have to do is input these various carbon allotropes into the Wine2K program, and the Wine2K program in return would give me the properties of each allotrope. So the first thing I did on the Wine2K platform was create the unit cell structures of each carbon allotrope. This involved basically creating the most basic unit of each allotrope, essentially the unit cell. And so I had to put in the coordinates of each atom of the unit cell, and the Wine2K program would refine these values to create a very symmetrical uniform structure. Then I would do something called initializing the calculations. And this is when the Wine2K program creates a computer code for each carbon allotrope. So in the previous step, I created the unit cell structures, and in the initialization calculation stage, the Wine2K program will convert those coordinates to a computer code. And then afterwards, in the SCF cycles, the program would use those coordinates to run my laptop CPU through a series of linear augmented plane wave functions, specifically the Cohen-Sham equation. And this basically produces the results, which is right here. So the results are basically, the results from the Wine2K program come in the form of band structures, and using the results from the SCF cycles and the initialization calculation stage, and created something called band structures. And a band structure is basically a graph that represents the states of energy that an electron can be in, the entire range of energies that an electron can be in. And this stage, the band structure stage, used the calculations from the SCF cycle stage to determine the energy levels of the conduction and valence bands. So once I ran this stage, I had my band structures. And just as a precursor to viewing the band structures, it's important to understand what exactly the band structures are. So each allotrope has a conduction and valence band. They essentially represent the range of energies that an electron can be in. And when the conduction and valence bands are very far apart, you have a very large band gap. And that band gap means that electrons can't travel very freely through the valence and conduction band. That means that when the conduction band and valence band are very far apart, the material we're testing is an insulator. However, on the other end of the spectrum, when we have the valence bands and the conduction bands very close to each other, electrons can travel very freely between two bands, and therefore we have a conductor. And a semiconductor is essentially a smaller band gap, but still one present, so electrons can sort of travel in between the bands, resulting in a semiconductor. So now here are my results. These are all band structures, as you can see. And just to provide how I analyzed each graph, as you can see here for the energy band structure of carbon, the band structure here has a small band gap. As you can see here, the conduction and valence bands have a small gap right here. And that gap was equal to, and that band gap was very small, meaning that the carbon here is an insulator. On the other side, graphite has no band gap because the valence and conduction bands are touching each other. So that means that the electrons can travel very freely in between each other, and therefore graphite is a conductor. So by running this same analysis for all these graphs, I was able to come up with the electrical type of each allotrope. And based on online databases, I was also able to collect the melting point of each carbon allotrope. And based on this data, I was able to determine a relationship between the melting point and electrical type of each carbon allotrope. So if you see here, the insulators generally have lower melting points. Amorphous carbon, diamond, and fullerene range from 280 degrees Celsius to 3,550 degrees Celsius. The semiconductor carbon nanotube was just slightly higher. The melting point was just slightly higher than the melting points for the insulators, and the conductors, graphite and graphene, had the highest melting points. So by looking at this data, I was able to realize that the insulating carbon allotropes had lower melting points, whereas the conductive carbon allotropes had higher melting points. While this is a promising conclusion, I do need more samples to make a solid conclusion. Since I was only able to test 4 to 5 carbon allotropes, there are other carbon allotropes I wish to test, such as carbon nanofoam, Lonsdaleite. The problem with testing these, though, is that their temperatures aren't recorded yet, since it's very difficult to test, since they're rather novel materials, rather novel allotropes. Their melting points haven't been recorded yet, so I haven't been able to run tests on them. So several other limitations of my study. The melting points of the allotropes were dependent on environmental pressures, so they're not all based on the same scale. While this is a concern, the temperatures all fall into general ranges, so I didn't really have to worry about small changes in the temperatures between elements based on different environmental pressures. Additionally, I ran this study to see if I could generalize the relationship in carbon to the material that most ESD mats are made out of. However, I do have to recognize that this relationship might only be unique to carbon. It may not be similar in other materials. So I do have to see how other materials would fare between melting point and electrical conductivity. And I will need to continue running tests on the Y2K platform on Linux for more carbon allotropes, and this will allow me to have a larger sample size to make sure that my conclusion still holds. So so as a last final note, my conclusion here of insulating carbon allotropes has lower melting points and conductive carbon allotropes has higher melting points basically gives an answer to my initial question of whether we can make ESD mats with higher melting points. And the answer is no, that we cannot have ESD mats with higher melting points because the point of an ESD mat is to be insulating. And the insulating carbon allotropes generally have lower melting points, which means that it's very difficult to create an ESD mat with a higher melting point, or it won't be able to protect against ESD. So I'd like to thank my professor, Dr. Nan Yao, as well as my research partner, Juno Lee, as well as the entire staff of the PRISM Imaging and Analysis Center in Princeton University. I'd like to thank the Liberty Science Center Partners in Science program for accepting me to participate in their summer program, as well as Ms. Finn, Mrs. Van Horn, and Dr. Brinkman for helping me throughout my 3 years in the science research program. I'd like to thank my peers in the science research program, as well as my family for supporting me throughout my journey. Questions? Okay, I have one question here. You mentioned being able to find a correlation between the melting point and conductivity. Was there any correlation between band gap and melting point? That's a good question. So band gap, I'll go back to the slide here. So as you can see, the band gap essentially represents the electrical type. So as the band gap got smaller and smaller, that meant that the material was more conducting. And this meant that the material was a conductor. So essentially, as the band gap got smaller, the melting point of the material was lower. But I don't. While that is a relationship, I don't think it's a causation. It is a correlation, yes. As the band gap got smaller, the melting point was lower, but I don't think that they cause each other in any way. Any other questions? Thank you for the question.
Montville Township Public Schools. Educate, inspire, empower.